Good afternoon, and welcome to the second day of the Kim Shine Festival. Uh, I'm going to give you a talk. My name is Dimitris, and I'm going to give you a talk about the safety of a nuclear reactor and if it produces energy in a safe and manner. So, what drives this research is the long and short-term changes in climate due to the increasing emissions of carbon dioxide as measured in the levels of it in the atmosphere. Like as you can see on the chart on the left, we have been consistently below that line, which of 300 parts per million, which we surpassed in the 1950s, and we keep increasing ever since. On the right-hand side, there is a YouTube video which can show the average temperature and how it changed during the last century or so. Up till now, we see some ups and downs, nothing too worrying. But after the 50s, it slowly becomes hotter and hotter and hotter and hotter, progressively, slowly but steadily, until we reach like the current date. So, climate change wouldn't necessarily be bad if not for the deleterious effects it has in our environment. This can be bad towards nature, but it can also be bad towards ourselves, towards humanity. For example, within nature-wise, we have like bleaching of corals in the seas. We have like wildfires because of the increased temperature that are more likely to happen. We have polar bears being starved to extinction pretty much because the polar ice caps are melting and their environment is basically being destroyed. But we also are affecting humanity because we cause things like drought, which affects crops and reduces the amount of food we can produce. And also it causes disaster to man-made environments, for example, due to floods in coastal cities like Venice in the image here. So one obvious solution is to use renewables to solve this energy problem, to reduce our carbon emissions, because renewables can generate energy perpetually and we don't run out of fuel. They are carbon free, so on the generation part at least, you have things like transportation and construction that will generate carbon, but that's like not a very big amount. We have multiple forms of them, so we can combine them to ensure sustainability. And we have 5 major sources, which are hydro, like waterfalls and dams, solar power, which we collect through the familiar to us solar panels now, wind turbines, which collect the winds and turn into electricity, geothermal energy, which is collected from geysers, which will also turn to heat and electricity, and tidal energy. We utilize the highs and the lows of the tides with arrays like this. However, there is a problem with this form of energy because of its intermittency. What it means, it's not always sunny. We don't have always wind. The tide's not going to be high all the times. So that causes a problem in how we can like ensure a steady supply of energy because our batteries, which we would have used to store the energy collected from these devices, are not yet capable of storing large amounts of power to meet the demand we have. And another example is the low density of it, because renewable energy sources are much less dense than carbon. They require much more land, as we will see. Which a prime example being, for example, Germany, where they had to cease the nuclear power plants and they had to resort to turning up the coal and the oil and the gas plants to cover for the demand. So how do we solve this? We can use nuclear. Nuclear is carbon neutral, at least in the energy generation. You still have emissions from mining, manufacturing, and transportation of the materials and the fuel, but this is the same for the renewables as well. It's also energy dense, as you can see on the graph on the right-hand side, where the acres, the amount of area required to produce a megawatt is similar between nuclear, gas, and coal plants, and much, much smaller than wind and solar and hydropower facilities. Also, because of its nature, it's very dense energetically, and because it's extensively regulated because of the dangers it may pose, there is very, very tiny room for deviation from humanity. So if we exclude the sources that require a lot of land and we exclude the carbon emitting sources, then all we have pretty much in the end is nuclear. So a bit of physics now. Chemical reactions are what we use to produce energy when we burn coal and gas. We burn hydrocarbons. That means we combine them with oxygen and then produce carbon dioxide and water. As an example, this image is like the burning of methane, which is like a common ingredient of natural gas. In chemical reactions, compounds may change, but the atoms will stay the same. A carbon atom will always be a carbon atom. It's not going to change. In nuclear reactions, however, this is not the case. Here, we change the elements themselves, either to a heavier or a lighter form, and produce energy as a byproduct of this conversion. The two major nuclear reactions are fission, where we use uranium, which we split into smaller elements, for example, kryptonite and barium, and to produce energy as a result of the process. And the other nuclear reaction is fusion, where we will join nuclei of hydrogen to produce helium and energy also as a result. This is how these two nuclear reactions can be seen in a graphical manner. Like on the left-hand side is the fission reaction, where a neutron will collide with a uranium nucleus, will split it into two smaller fragments and 2 or 3 neutrons as well. And this in turn will go to further uranium nuclei and cause further fissions, creating a chain reaction and propagating the whole process. On the right-hand side, there is a schematic of a fusion reaction where 2 hydrogen nuclei are being joined together to form a helium nucleus and also to generate energy. So we have seen the reactions behind, but how does the reactor look like? A brief schematic is something like this. In the reactor vessel, it's where the fuel is being found. And the fuel, being uranium, undergoes fission, the reaction we saw in the previous slide, and creates heat. This heat is being collected by the coolant, the primary coolant, which is now, this case, is like water, which we ensure that will stay in this design, that will stay liquid all the time through the use of a pressurizer. That water will heat a secondary circuit, and the use of like 2 circuits is because we don't want this water to be contaminated by the water in the primary circuit. The water in the secondary circuit will boil, turn into steam, go and rotate turbines, which are connected to generators, which then supply electricity to the grid. The water from the secondary circuit then will be cooled from water from a tertiary circuit, like a lake or a river or the sea nearby the nuclear plant, and will return back into the reactor to extract further heat. This design we saw is known as a PWR, a pressurized water reactor, because we use water as a coolant, and we pressurize it to avoid it being boiled on the primary circuit at least. It's a type of a fission reactor which split uranium into smaller nuclei, as we have seen. However, we need to slow down these neutrons to maintain a constant chain reaction. We do that using a moderator. A moderator is a material that will slow down the neutrons to speeds suitable to induce further fissions. Now, in water reactors, the water will also act as a moderator in addition to coolant, so that design is pretty much sorted itself out. We can use, however, other materials such as carbon, such as graphite, which is what we use as a moderator in the advanced gas-cooled reactor, which is what we currently utilize in the UK. An image of the left is Hinkley Point B, a reactor of a gas-cooled reactor in Somerset in southwest England. And on the right, there is a small schematic of how that reactor works. In essence, it's a similar process. Instead of water, we have graphite to moderate the neutrons and ensure the chain reaction, and we extract the heat using carbon dioxide, which will then have that heat transferred to a secondary water coolant, which will then turn into steam, rotate the turbine, and create electricity. So we have covered the fission reactions. So what about the other reaction? It's the fusion one. Fusion is essentially the adjoining of light atoms such as hydrogen, and it's what the sun and the stars use to power themselves. However, to do that, we need massive amounts of power and temperature. Like the temperatures required to achieve fusion are in the order of tenths or hundreds of millions of degrees centigrade. So how can we achieve that on Earth? We can achieve that using devices like this. This is called tokamak. It's essentially a toroidal construction in which we compress this gas of hydrogen to make it undergo fusion to very large pressures and very high temperatures. It's a bulky design. I'm not going to go further into that because my colleagues will talk about it in a later talk today. So up till now, we have covered the ways we can produce energy, but is that safe? As regards the fission reactions, it is, but for numerous measures. One of them being the control rods. The control rods are essentially the gas and the brake pedals of the reactor. They're made of materials that can absorb neutrons. So by putting that rod in, we slow down the reactor. By pulling that rod out, we accelerate the production of energy. And we'll put it fully in if we want to stop the production whatsoever. The second safety measure we use is to achieve redundancy. Essentially, we will have backup choices if something goes bad. If, for example, we need 2 cooling pumps, then for a specific design, we will make sure to have 4 of them inside, so that if 2 of them are broken and cannot function, the other 2 can step in and cover for that. Other safety measures we can use is to separate the radioactive, the non-radioactive parts. That's why we have like 2 or 3 cooling circuits. And we also put everything that's active in nature in the a region called the nuclear island, which basically isolates the active parts of the plant from the non-active parts. This can be seen in further detail in that image over there, where basically the reactor core and everything that has is used to utilize fuel is basically on one side of the image and in one specific region of the plant, whereas everything else that's not active by nature is on a separate area. Another concept we use is negative feedback, where basically we utilize several phenomena which can help us to rebalance things. An example in water reactors is because the water is also the moderator, if the reactor power is increased, it will create more heat. This heat will cause the water to dilate. And because the water will be more dilated, less neutrons will be likely to collide with the water molecules and be slowed down. As a result, our power will be decreased and the reactor will balance itself out. However, there are cases where this might not be the case. So we have like the ultimate step if something like that happens, which is basically to scram the reactor. Scram is an acronym that means Safety Control Rod Axeman, and will basically put the control rods inside the reactor and stop the reaction immediately. And the name comes because in the very first experiment of nuclear fission, which is that pile you can see on the left-hand side image over there was actually a man with an axe waiting to cut the ropes that were connecting, that were holding the control rods, if need be, and stop the reaction in an emergency. But we don't use an axe now. Just use like this pattern over there, which is an image of a control room of a certain nuclear reactor. So to conclude, is nuclear reactor safe? Environmentally, it is because it requires much less land compared to renewables. It emits much less CO2 compared to fossil fuels, and the waste problem can be sorted by burying them into deep geological repositories. Financially, it can assist in energy production because it will reduce electricity cost, because it will increase energy supply, and can create new jobs, both in construction, maintenance, and operation phases of the plant, as well as decommissioning. And the risks it carries can be mitigated if we combine the nuclear power with renewables, which also do not emit CO2. So, and this is probably the best chance we have to tackle climate change. And that will be the end of my talk. Thank you very much for listening, and I'm happy to answer any questions.